In this video, we're deriving an expression for the intensity delivered by a sound wave in terms of the sound pressure. In other words, we're going to find the power per unit area when that sound wave arrives at the eardrum, and we also throw in an additional result on how the intensity varies with distance from the source. And then we wrap things up with an example at the end. And this time, we're going to have to pull together so many previous results that I decided to start by just summarizing everything that's going to be useful in the derivation, and I'll just post links to the corresponding videos as I go. So first, as we can see in the animation, sound is a longitudinal wave, and that means the particles in the medium move back and forth parallel to the direction of wave propagation. And the amplitude of that oscillation is called the displacement amplitude of the medium. And we can describe the displacement of the medium by a function of position and time that I'll call the displacement wave function. So that's given by y of x and t is a cosine kx minus omega t if we're talking about a rightward moving wave. And remember that that wave speed is given by omega over k. Now in the previous video, we used this displacement wave function to derive the corresponding pressure wave function. And that's given by p of x and t is equal to b times a times k times the sine of kx minus omega t, where that b is the bulk modulus of the medium, a is the displacement amplitude, and k is the wave number. And this immediately implies that the maximum pressure value is just equal to the amplitude of that pressure wave, and that's just b times a times k. And then finally, we need to use the fact that the speed of sound as a sound wave travels three-dimensionally in a material is given by the square root of the bulk modulus divided by the density of the medium. Okay, so now we're ready to look at the energy issues in a sound wave and derive our expression for intensity. So we're setting out to find the intensity of a sound wave arriving at a particular location. And just a quick reminder, intensity is power per unit area. So that's measured in watts per square meter. And there's a little reminder of the displacement wave function and the pressure wave function for the sound wave. We're going to need those. And what we're looking at in the picture is a column of air with a cross-sectional area of A. And one tiny slice of air is highlighted. And that slice has an equilibrium position of x, and it's currently displaced from that equilibrium by a distance of y. And again, that displacement is a function of time as well, and it's given by our displacement wave function y of x and t. Now this little slice happens to be feeling a force of F perpendicular right now, and it's moving with a velocity of v of x and t. So to find the power delivered by the sound wave coming from the left at this particular instant, we use our classic formula power equals force times velocity. And that force is just our F perpendicular, and the velocity is a function of both x and t. That's v of x and t. But we can rewrite that force as pressure times area. And while we're at it, we'll rewrite the velocity function as the time derivative of the displacement wave function. So again, in those first two terms, I just took the pressure and I multiplied by the area to get the force exerted on that little slice of air. And then the time derivative of y gives us the velocity as a function of time and position. So we're going to sub in the formula for the pressure as a function of position and time. And we need to take a derivative of y of x and t with respect to t. So note when I take the derivative of this function, differentiating the cosine produces a minus sign, but the chain rule produces a factor of negative omega, so those minus signs cancel. And the derivative of that guy is just a omega sine kx minus omega t. So I did a lot all at once here, but I see over on the right-hand side an a omega sine kx minus omega t. That's that time derivative. And on the left, I see that pressure function as a function of x and t. And what I did at the same time is divide both sides by that little a. That gives me power divided by area, which is intensity. So we immediately have an expression for the intensity as a function of position and time. So we're just going to clean things up a little and collect those two factors of that sine function. And we also have two factors of amplitude. And we arrive at this expression for intensity, b times a squared omega k sine squared kx minus omega t. Now we want to eliminate the wave number here. And we can do that using the relationship that v is equal to omega over k, which then implies k is omega over v. And we're also going to sub in the fact that the speed of sound is the square root of bulk modulus over density. So when I replace this k with omega over v, I arrive at this expression. B times a squared, omega squared over v sine squared kx minus omega t. But then I replace the v with the square root of bulk modulus over density. So that's going to put a square root of bulk modulus in the denominator, which then leaves only a square root of bulk modulus in the numerator. And dividing by that v is also equivalent to multiplying by a square root of the density. The net result there is that out in front, we have a square root of bulk modulus times density. The a squared is still hanging around, and the omega squared is still hanging around. And that's all multiplying sine squared kx minus omega t. Now, one important note here is that this intensity is proportional to the square of the displacement amplitude, and that should be familiar. It's the same thing we saw with energy delivered by a one-dimensional wave on a string. So there's our intensity as a function of position and time being delivered by this sound wave, but we're particularly interested in finding an expression for the average intensity. And along the way, we'll find an expression for the maximum intensity. So that's just the amplitude of that function. So square root of b times rho times a squared omega squared. Now the calculation of average value is non-trivial. You have to compute an average value integral of the square of a sine function. But we just did this recently when we were working with one-dimensional waves, and the result is that the average of a square of a sine or a cosine is just 1/2. So we end up with this expression for the average intensity delivered by the sound wave. It's 1/2 square root b rho times a squared omega squared. Now the last thing we want to do is express this in terms of the sound pressure instead of the displacement amplitude. So there's our expression for the average intensity in terms of the displacement amplitude. In other words, the actual physical wiggling of the air molecules. And we want to reformulate this in terms of pressure. So we go back to this relationship between the maximum pressure of a sound wave and the displacement amplitude. So P is equal to B times A times K. And we just have to solve for A there and sub it in. So A is just P over BK. And we replace it in our expression for the average intensity. And note that when I square this term, I'm going to end up with a k squared in the denominator, but omega squared over k squared is just the wave speed squared. So that k is gone, the omega is gone, and I have a v squared. But v is just the square root of the bulk modulus over the density. So again, omega squared over k squared is just v squared, but v squared is b over rho. So there that is in our expression. And we still have to square this bulk modulus in this denominator. That's going to cancel one factor of bulk modulus, but it leaves us with one factor of bulk modulus in the denominator. So we have one factor of bulk modulus in the denominator and one factor of density in the denominator, and we have the square root of those things in the numerator. This leaves us with the square root of both of those terms in the denominator. So our average intensity boils down to a 1 over 2 square root b times rho times p max squared. And that's really the main prize that we were working toward here. We have an expression now for the average intensity delivered by a sound wave in terms of the maximum sound pressure. And these are the things we actually care about measuring. We don't ordinarily care about measuring the actual displacement amplitude for the wiggling air molecules. Okay, so that was the major point of the video, but we have one side quest to complete, and that's looking at how the intensity of a sound wave drops off with distance to the source. So what we're viewing here is just this very ideal circumstance where I have an isolated sound source emitting sound waves three-dimensionally, and that wavefront is going to spread spherically around that sound source at the speed of sound. So as that sound wave spreads out, the energy is being distributed over a larger and larger area. And that means the intensity, or the power delivered per unit area, has to drop off like 1 over r squared. To be a little more specific, the intensity is going to be the power emitted by that sound source divided by 4 pi r squared, because that's the surface area of a sphere. Okay, so we figured out how the intensity drops off with distance, and now we can wrap it up with an example. So in our example, we're told that we have a sound source emitting a pure tone with a 300 watt average power output. In part A, we're asked to compute the average intensity of the sound at a distance of 8 meters from the source. And then in part B, we're asked to find the maximum sound pressure for this wave. Now to get that done, we also have to be given numbers for the bulk modulus of air and the density of air. So to get the average intensity, we're just taking that total power and spreading it over the given amount of area. So just to go back to fundamentals here, it's power divided by area. The total power output of this wave is 300 watts. And at a distance of 8 meters, that's spread over the surface of a sphere with a radius of 8 meters. So that's 4 pi times that radius, 8 meters, all squared. And when I run the numbers on this to 3 significant digits, I get 0.373 watts per square meter. So then in part B, we want to find the maximum sound pressure for this wave. And so we're going to use that relationship we derived. The average intensity is 1 over twice the square root of the bulk modulus times the density times our maximum pressure squared. So that P max is the thing we want to solve for here. So we need to multiply both sides by 2 square root B times rho, and then square root the result. So just solving this symbolically, P max is going to be the square root of 2 times our average intensity times the square root of B times rho. So we sub our numbers into this expression, and we have an average intensity at this particular distance from the sound source of 0.373 watts per square meter. Then our bulk modulus for air was given as 1.42 times 10 to the 5th. That's measured in pascals, by the way. And then we have a density for air of 1.29 kilograms per cubic meter. And when I run the numbers on this to 3 significant digits, I get about 17.9 pascals. So in practice, the range of intensities of sound waves that humans can perceive with our ears is so enormous that people use a logarithmic scale for describing the loudness of sound instead of using these SI units of watts per square meter. That's called the decibel scale. And in the next video, we learn why we need a logarithmic scale for studying the loudness of sound waves, and we define the decibel, and we learn how to do some common calculations with decibels. I'll post a link to that video at the upper left, and I'll see you there.